Magnetite is a magnetic mineral. It's an oxide. It means it ends in oxygen. So the formula is, it has ferric and ferrous iron and oxygen, which is why it's actually magnetic. This mineral is isometric. It's actually much, much harder than ulexite. It's got a hardness of 5.5 to about 6.5. It's got a very high specific gravity of about 5.175. So it's dense. It's very, very dense. And it's because it's got a lot of iron in it. It's got a lot of iron. Iron is much heavier. It's magnetic. It's opaque in thin section and in hand sample. So it's not translucent, not transparent. It's got metallic bonds, so that makes sense, right? It usually contains some titanium, and the titanium can replace in part of the iron, and it does form a complete solid solution series with another mineral called ulvospinel. Yeah, that's exactly right, Virgil. That's what I just pulled up. Yeah. It forms a complete solid solution series with ulvospinel. And looks like not very many hand samples are common. That's cool. These are really pretty SEM images. Which is titanium, iron, and oxygen. So you can see it's just got a little less iron and a little more titanium. They're both very, very high in specific gravity. Hardness is a little less, though, on the ulvospinel. Octahedral crystals are common, like you see here. Very, very, very cool. I love them. I love them a lot. Usually, there is no cleavage. Unlike ulexite. Ulexite had 3 planes. One was poor, one was good, and one was perfect. Magnetite has no cleavage at all. All the crystal forms you see here are its actual shape, its habit. That's how it grows. So it fractures unevenly. It doesn't fracture conchoidally like quartz does. It fractures just in uneven ways. Dodecahedrons. It can form dodecahedrons as well. So that's what we're seeing here. That's really cool. That's really cool. I mean, this isn't as common. The octahedrals are much more common here. Go on. This mineral is actually brittle, unlike ulexite, which was flexible. It's dull metallic to splendid in luster, which makes sense because it's a metallic mineral. It does have a black color, obviously. You can see that. It's just the shininess that makes it maybe kind of appear gray, but it is actually black in color. Its streak is also black. You could pulverize it. It would be black. In fact, it's actually used and has been used for pigments in the past because of that. It is opaque in thin section as well as in hand sample. I think I already mentioned that. It can alter to hematite or goethite, which is another couple of iron oxides. Hematite can actually, there's some potential exsolution lamellae with ilmenite, but it otherwise can't alter to ilmenite. It's common in igneous and metamorphic rocks, but it's not so common in sedimentary rocks. It's considered an accessory mineral in igneous and metamorphics. And that means it's just not super, super common, but it is common enough. It's just not one of the rock-forming minerals like plagioclase or potassium feldspar or quartz. It's considered an accessory mineral, and it can be found in sedimentary environments. It just doesn't last as long there. So yeah, in areas with limited chemical weathering, you can find some magnetite grains. It's just not, it's going to be limited to areas with limited chemical weathering. These grains they can range from anhedral to euhedral, so they can be really, really well developed, or they can be completely fractured and have total uneven surfaces. It depends on the energy in the environment and how much weathering has occurred on that specific mineral. We basically went over all the physical properties, but I haven't not gone over the uses and a bit of the scientific background of this mineral. The uses of this mineral. Well, it's mined as an ore for a metal. I wonder what metal it's mined for. It is iron, yes. Absolutely, it's iron. It's obviously mined for iron. I mean, we need it. We use it, and a lot. It's one of the things we use in steel. It's used as a black pigment, like I've mentioned. Obviously, magnets. It's used as an aggregate for high-density concrete for applications that have included nuclear reactors. How does it form? Forms in volcanic rocks. So, yeah. That's what we're going over next. So, this is where it gets interesting. This is where magnetite gets really, really interesting, and this is why I voted for magnetite. It provides evidence for continental drift and for tectonics. And here's how. Magnetite can acquire and preserve a magnetic polarity under the influence of an external magnetic force. Well, we have one on the Earth. And there's a magnetic field that surrounds the Earth. We have a north and a south magnetic pole, and it wavers, right? There's magnetic north, and then there's the North Pole. They're very, very different locations. They can be the same depending on the time and the age of the Earth and the history of the Earth. But right now it is, I actually don't know the declination off the top of my head currently. And it does depend on where you are in the world, what you have to set your declination and your compass to. So it's something to actually be aware of if you do like hiking a lot and you use compasses, or you want to go backpacking off the beaten path. Make sure to know that you are in a specific location on the planet, and that magnetic north needs to be changed depending on where you go. Magnetite actually forms in volcanic rocks. So the small grains will become magnetized parallel to the Earth's magnetic field when it cools through the Curie temperature. So above the Curie temperature, it won't preserve that magnetic field. So if you've got a piece of magnetite and it is heated above that temperature, whether or not it melts, that magnetic signature is erased regardless. So it preserves whatever, it would remelt, but it'll preserve the magnetic signature. And then what you can do with it is, if you know the date of the rock in which it's contained, because dating igneous rocks is fantastic, and we can do that using radiometric dating. So radioactive elements, radioactive isotopes, we can figure out via their parent and daughter their parent and daughter products, and determine an age of that rock, because the Earth is very, very old. Well, we can then use that magnetic mineral, or multiple minerals, and we have the direction of the magnetic pole at that time, and then we also have a date to put to it. If we have many samples of these, so we have a dates, and so we know, oh man, 100 million years ago, the magnetic poles were reversed. I'm just arbitrarily saying that. Don't know if it's true. Arbitrarily creating a situation. Well, you can actually then figure out, based on the ages of the rocks that you're dating and the magnetic polarity, and determine where and how the continents shifted over the age of the Earth. And the magnetism can actually be preserved for long, long periods of geologic time. Long periods of geologic time. And it's measured with a magnometer. So, again, with radiometric dating, the Earth's magnetic polarity and the distance direction to the magnetic poles for that particular time can be determined. And then we can use that to unlock how the plates have moved, where they were, because we know at that time where the magnetic poles were, because we can radiometrically date things. So it does take two things. It takes geochronology, or radiometric dating, and it does take understanding paleomagnetics, which is an entire field of geology. Paleomag, interestingly, the master's program that I went to, there were a group of people doing paleomagnetics, a group of people doing climatology and paleoclimate. And then there were a group of people doing carbon capture, sequestration, and sedimentology, and that was me. I was doing the carbon capture, sequestration, sedimentology, geochem stuff. And then there were oil people, there were hydro people, but we did have a group of paleomag students, and they did produce quite a bit of really cool papers. If you are ever taking a geology course and you have to ID minerals, make sure just to test them all with a magnet, because if you have magnetite, it's all, yeah, magnetic, done. You know what it is, done.